You're listening to The Star Spot, episode 180 for Sunday, March 29th, 2020.
I'm Justin Trottier, and I'll be your host of The Star Spot. The Star Spot is a space-themed podcast that focuses on all aspects of astronomy and space exploration. Episodes feature interviews with guests of wide-ranging backgrounds: scientists, engineers, educators, artists, politicians, and business people. Topics are similarly broad, from the latest space mission to how the universe began, from why humans explore to how we can make exploration economical. We'll also include a segment called Current in Space, bringing you reports on news and developments that may interest the space enthusiast. You can now find the show on Facebook at facebook.com/thestarspot or follow us on Twitter at thestarspot. We would like to thank Western University's Department of Physics and Astronomy and the Hume Cronyn Memorial Observatory at Western University for their generous sponsorship of the show. You can visit our sponsorship page at www.thestarspot.ca to find a link to their websites where you can learn more about their research and upcoming events. They are the stuff of science fiction, but wormholes are also the subject of intense scientific debate. Can wormholes provide a mechanism for faster-than-light travel through space? And, even more intriguing, do they open the door to travel through time? Today we're joined here at the Star Spot by one of the world's foremost authorities on wormholes, Professor John G. Cramer, to share results from his thought experiments on wormholes and his laboratory experiments aimed at changing the past. But first, here's what's current in space.
Using new radio data, astronomers have confirmed an unusual phenomenon near the center of the Ophiuchus galaxy cluster, 390 million light-years from Earth. A large cavity in superhot gas at the center of the cluster appears to be a fossil of the most powerful active galactic nucleus outburst that has ever been discovered. Galaxy clusters are large collections of galaxies, dark matter, and gases so hot that they emit X-ray radiation. At the center of the Ophiuchus cluster is a supermassive black hole, which can contain 1 billion times the mass of the Sun. Gravitational forces and friction cause surrounding material to spiral in towards the black hole. This infalling material contains ionized particles, which are accelerated out of the black hole's axis of rotation as jets. This collective structure is an active galactic nucleus, and these jets are believed to have been responsible for carving out the cavity in the gas. In 2016, astronomer Norbert Werner detected an extremely large cavity using X-ray data, and his team theorized that the hole was created by an active galactic nucleus outburst. However, they discounted the theory, as it would have required enormous amounts of energy. Astronomers from the Naval Research Laboratory and the Goddard Space Flight Center have taken this X-ray data and analyzed it in conjunction with new radio data. They have published a paper in the Astrophysical Journal confirming that the cavity was indeed caused by an active galactic nucleus outburst, the largest ever observed. An explosion of this size is unprecedented. The authors of the paper estimate that the energy required to create such a cavity would be 10 to the 54 joules, 5 times more than the previous record holder. To get some perspective on just how much energy this is, 1 ton of TNT releases 10 to the 9 joules, and worldwide energy consumption in 2013 was 10 to the 20 joules. The black hole would have had to swallow 270 million solar masses of material, possibly over 100 million years. A mystery still remains. Typically, active galactic nuclei produce jets from both rotational poles of a black hole. However, radio emissions are missing from one side of this one, and it is unclear as to why this is the case. Combining data from X-ray and radio telescopes has led to this incredible discovery, but even more data will be needed to answer remaining questions.
NASA's newest rover won't be nameless. The new robot being launched this summer has aptly been named Perseverance. Even more heartwarming than the name itself is the name's origin. As with the naming of all rovers before it, NASA held a nationwide contest asking for students to submit their name ideas for the newest rover. The contest began early last year and raked in over 28,000 essay submissions. This massive first pool was whittled down to 155 semifinalists, which were then cut down further to 9 finalists this past January. Those 9 finalists included 3 proposals from each of the 3 age categories: kindergarten to grade 4, grades 5 to 8, and lastly, grades 9 to 12. NASA encouraged the general public to vote for their favorite name out of the final 9 options, but the decision was ultimately made by Thomas Zurbuchen, the Associate Administrator of NASA's Science Mission Directorate. Zurbuchen announced the name of the new rover at a name unveiling ceremony held by NASA this past week. The name Perseverance stood out to Zurbuchen for a very specific reason. He was quoted at the ceremony as saying, "There has never been exploration, never been making history, without perseverance." Perseverance is a strong word. It's about making progress despite obstacles. NASA has let school children name all of its Red Planet rovers to date. The winning submission was proposed by Alexander Mather, a 7th grader from Lake Braddock Secondary School in Virginia. Mather read his essay during NASA's name unveiling event. He declared his love of space and science, adding that he plans to carry these passions through his entire life. As he proposed the winning submission, Mather will get a free trip to Cape Canaveral, Florida to watch the launch of Perseverance this July. Perseverance will land on the Red Planet in February 2021, its primary mission being to search for signs of life on Mars. Kicking off a $2.5 billion mission, this is the first time a NASA service craft has hunted for possible Martians since the twin Viking landers did so in the mid-1970s. Perseverance also has 23 cameras and 2 microphones, which might allow us to hear the sounds of Mars for the first time ever. Scientists are hopeful that Perseverance will bring the answer to a question that has been asked for decades. Could there be life on other planets?
A black hole could be friendlier than you might expect. Despite their reputation for devouring anything that goes into them, black holes are really just another source of gravity, like a star. So it's possible that planets could orbit black holes, and amazingly, they may even sustain life. Despite the name, most black holes are among the brightest objects in the universe, because gas and other matter falling in is superheated and glows as it accretes. Compared to this chilly character, the rest of the universe is relatively balmy, about minus 270 degrees Celsius, thanks to the cosmic microwave background, the heat left over from the Big Bang. An Earth-sized planet orbiting a black hole that appeared a similar size to our Sun in the sky could extract around 900 watts of useful power from this temperature difference, enough for life to potentially exist, but hardly enough to run a civilization. But for life to be possible at all, the black hole would need to be large, at least 163 million times the Sun's mass. That's because smaller supermassive black holes like the one in our Milky Way, weighing in at 4 million times the Sun's mass, tend to rip stars or planets apart with tidal forces as they approach. Around larger black holes, tidal disruption doesn't happen until a star or planet is inside the event horizon, so anything outside is safe from that fate. It would certainly be no place like home. The deep blackness of the event horizon looming over nearly half the sky would be a forbidding presence. And because of the time dilation effects in Albert Einstein's theory of general relativity, 1 year passing on such a planet would see thousands of years go by around an ordinary star. Even if life could take hold on such a world, there is little chance of detecting it. A planet passing in front of a black hole isn't going to make it appear any dimmer when it's black already. However, astrophysicist Pavel Bakala of Silesian University in the Czech Republic says a vast array of radio telescopes, like the one used in 2019 to image a black hole for the first time, might be able to detect such a transit. So any planet that lives close enough to a black hole will be warmer than usual, and if you're a planet, you might just find your water ice converted into liquid water oceans, a potential home for life. Life will eventually have to emigrate to planets around black holes once all the stars die out, but that won't be for around 100 trillion years. Even then, it's more likely that any future beings will absorb life from accreting matter rather than dwell under a cold sun, as by then, the cosmic microwave background will have faded into nothing. According to astrophysicist Lawrence Krauss of Arizona State University, when the stars are gone, black holes will be a last resort source of energy. But for the practical future, there are much easier ways to live than that.
Katherine Johnson was a wonderful mathematician who worked on countless NASA missions from the 1950s to the 1980s. She passed away on February 24, 2020, but her story will be an inspiration to many. In a time when women, especially women of a minority group, were suppressed, she was able to rise above limitations to pursue a career devoted to her love of math. Johnson was born in 1918 in White Sulphur Springs, West Virginia, and was the youngest of 4 children. She was an exceptional student throughout her academic years, always excelling in anything related to math. The racial discrimination that existed in her hometown forced her family to move in order for her to attend high school, from which she graduated at age 14. She then went to West Virginia State College, where she graduated at 18 with degrees in both math and French. After graduating college, Johnson became a teacher and taught for several years before she was accepted into West Virginia University's math graduate program. In 1939, she became the first Black woman to attend this program. A year into her graduate work, she left to take care of her 3 daughters. Fortunately, in 1952, she was told about NACA, now NASA, hiring Black women to work as computers, the humankind. She applied and was soon hired at Langley Research Center to work as a computer to calculate flight test paths. This began her extensive and dedicated career with mathematics and NASA. Johnson worked a long and committed career with NASA, all the while dealing with the prejudice that she was subjected to for being a Black woman. This was during a time when non-white workers had to work, eat, and use restrooms separate from the white workers. However, Johnson ignored these barriers and was able to accomplish tremendous achievements while working for NASA. She calculated the trajectories for NASA's Mercury mission in 1961, including that for the first American to reach space, Alan Shepard, and later the first American to orbit Earth, John Glenn. She also aided some of the Apollo missions by providing calculations for Apollo 11 and 13. She made calculations to allow the Apollo 11 lunar lander to sync with the Moon Orbiting Command and Service Module to get the astronauts back to Earth. She provided backup procedures to ensure the Apollo 13 crew's safe return after the craft malfunctioned. Johnson was also the first woman in the Flight Research Division to be credited as an author on a research report. She later went on to co-author 26 research reports before retiring in 1986. After retirement, she delivered many inspirational talks to students about her career and encouraged them to pursue STEM-related careers. In 2015, she received the Presidential Medal of Freedom by President Barack Obama. The following year, Johnson received special attention from the entertainment world, being portrayed by actress Taraji P. Henson in the Oscar-nominated film Hidden Figures. Mere months before she died, she received the Congressional Gold Medal. 2 NASA facilities, the Katherine G. Johnson Computational Research Facility in Hampton, Virginia, and the Katherine Johnson Independent Verification and Validation Facility in Fairmont, West Virginia, are named for her.
And that's what's current in space. The Star Spot is a volunteer-run organization. We operate with lots of love and a passion for astronomy, but that doesn't quite cover all of our needs all of the time. Costs from web hosting, recording space, speaker fees, conference coverage, and printing flyers, posters, business cards, and the like do add up, which is why we have decided to join Patreon. Patreon is a simple way that fans of the show can contribute to the podcast every month and get some great rewards in return. Please check out our Patreon page at patreon.com/thestarspot. That's patreon.com/thestarspot. You can also find a link to that page on our website. Thank you very much. John G. Cramer is Professor Emeritus of Physics at the University of Washington. He has made contributions to the relativistic heavy ion collider project at Brookhaven National Laboratory and the particle accelerator at CERN. He is known for his experiments in quantum retrocausality, which explore the possibility of effects preceding causes. Cramer is a regular guest on the Science Channel and NPR, and he has authored multiple books of hard science fiction. Well, I'm absolutely delighted to be joined here today at the Star Spot by Professor John G. Cramer. Thanks for being on the show.
My pleasure.
You gave a very intriguing presentation to the Astronomy and Space Exploration Society at the University of Toronto. I believe it was a couple of months back now, on the topic of
End of last month, yeah.
Just last month. Oh, well, these days it feels like every day is like a week or more. Pardon me, but the topic was wormholes. I've never talked about wormholes here at the Star Spot. Maybe you could just define for us, what is a wormhole for those who haven't read any science fiction or seen any science fiction films?
Okay, this is an idea that was originated by Albert Einstein and his colleagues in about 1935. Basically, Einstein was disturbed that particle physics couldn't be included in the framework of general relativity, and he was looking for a way to do this. And he and his colleague Nathan Rosen of the Princeton Institute for Advanced Studies discovered that you could have a sort of a transspatial connection between one part of space and another through a sort of a little tunnel. And they hypothesized that if electric lines of flux were threading through such a tunnel, it would look, one end of it would have positive lines of force coming out and the other end would have negative lines of force going in. And so the going in end would look like an electron and the coming out end would look like a positron. And so they were hypothesizing that maybe the fundamental particles, in particular electrons and positrons that we see in the world, might be the two ends of wormholes that are threaded by electric flux. And this became known as an Einstein-Rosen bridge. And people in the physics community sort of scratched their heads and didn't know what to make of it for a long time. And then shortly after the war, John Wheeler and one of his colleagues investigated this idea more thoroughly. And Wheeler awarded he didn't much like calling it an Einstein-Rosen bridge for some reason, or renamed it wormholes because he thought it was more descriptive of what was going on. And he and his colleagues figured out that if there was such an object in the world, first of all, it would have a mass that was much larger than an electron or a positron. And secondly, it would be dynamically unstable, that it would, if one happened to appear in space-time, it would pinch off and disappear so fast that you couldn't even shoot a photon through it. And so the physics community kind of relaxed because they were worried about this being some kind of strange thing that would violate some of their prejudices about how fast you could send information. And it stayed that way for a long time. And then Carl Sagan got into the act and things were dramatically changed. You know the story about Carl Sagan and wormholes?
I know the story of Contact, where the wormhole figures prominently as a narrative device. That what you're referring to?
Yeah, Carl Sagan wanted to use, he got a rather lucrative book contract to write a science fiction novel. And so he was sort of fishing around for what sort of thing to use in the plot. And he hit upon the idea of wormholes, and he was very disturbed that when he checked the literature, he found that they were unstable and couldn't be used for anything. And so he went to a friend of his, Kip Thorne, a professor at Caltech, who was a specialist in general relativity, and one of the guys who recently won the Nobel Prize for the discovery of gravitational waves.
Mm-hmm.
And he asked Kip Thorne if there was any way at all you could make stable wormholes. And Thorne had not thought of this, and he considered it a very interesting idea. And so he got one of his graduate students, Mike Morris, to take this on as a project and investigate whether there was any possible way you could stabilize wormholes. And rather to his surprise, Mike Morris came up with a way of doing it, which is that you can do it by providing negative mass energy in the mouth of the wormhole. Now, the trouble with that, I mean, that sounds great, except that we don't really have much negative mass energy around. But there is an artifact in the physics literature where negative mass energy is actually present, and this is something called the Casimir effect, where if you have two electric plates spaced very close together, the modes between the plates electrically conducting the modes between the plates that have a wavelength that's longer than the spacing. The plates are damped out, and so the space-time energy goes down and actually becomes negative. And so Morris and Thorne and a postdoc named Yurtsever came up with the idea that you could have two spheres, which were essentially Casimir plates, one end of one wormhole mouth and the other in the other wormhole mouth. And if you spaced them properly and held them in place properly, you could get enough negative energy to stabilize a wormhole. And so they published a couple of papers, in which they proposed that an advanced civilization, of which we are not one, we are not an advanced civilization in the terms they were using, could somehow snatch an incipient wormhole out of the quantum foam, pay off its debt to Heisenberg by giving it enough energy to exist, and stabilize it by using this technique. And then they further went on to investigate a way in which you could convert wormholes into time machines.
So just before we get to that, because I have obviously a lot of questions about that aspect of using wormholes as time machines, but I want to understand what would be needed in theory to create a wormhole. You just said negative energy. That's the main thing you need. That's the only thing you need. Are there other requirements?
Well, first of all, you have to have a wormhole to stabilize, and the way, and it's not exactly clear how you could sort of spontaneously curve space enough to do that. But what Morris and Thorne decided was that if you look at small enough distances in the quantum vacuum, there are all kinds of fireworks going on where various things are being created and annihilated almost immediately. Usually things like photons and electrons and positrons, but possibly other things. And there's an Australian physicist named Matt Visser. He's sort of a friend of mine who had an alternate way of providing the negative energy that was needed. Wormholes are a solution of Einstein's equations of general relativity. And there's another solution in general relativity that people have played with for various reasons called a cosmic string, which is sort of a one-dimensional object that goes through space. And if you measure the number of degrees as you go around it, it turns out to be either greater than or less than 360 degrees, depending on whether the cosmic string has positive energy or negative energy. And Visser hypothesized that you could have a little loop of cosmic string that had negative string tension and was therefore trying to expand. And if you put this in the mouth of a wormhole, and it would have negative energy, and if you put this in the mouth of a wormhole, which is trying to contract, the two could cancel one another out. And so perhaps during the Big Bang, for example, when various things were being created and destroyed, there might have been a wormhole in a cosmic string that made a happy alliance and became a stable wormhole. And so this is an alternative way of having a wormhole that looks a lot more transversable than the Morris Thorne idea, because in their idea, these big Casimir spheres would get in the way and make it very hard to go from one place to another, whereas in Visser's idea, the wormhole would be sort of framed by a loop of cosmic string, and there wouldn't be anything in the way to get through it.
So we have a few different variations on what a wormhole how a wormhole might have originated and what its sort of properties would look like today. How would we look for one or the other of these variations of wormholes?
Well, this is a sort of an interesting story. There was a NASA manager, I can't remember his name, who was getting ready to retire, and he still had some at Caltech, at JPL, and he still had some perks about what he could do, and he was a science fiction fan, and so he enlisted me and Gregory Binford and Jeff Landis and Bob Forward to come to JPL and meet with Mike Morris, who was the graduate student I mentioned, of Kip Thorne's, and Matt Visser, the guy with the cosmic strings, and some NASA people it's for a workshop where we spent 3 or 4 days talking about wormholes and what the possibilities were and so forth and so on. And the NASA generated a report on this. And while we were there, we had an idea, which became a paper in the physics journal Physical Review D. The idea is this: okay, suppose that, as Visser had hypothesized, there were wormholes that were created during the Big Bang and are still out there. Okay, you have 2 wormhole ends, and they're presumably in 2 different places. Presumably during the Big Bang, one of these places might be in a place where there was a lot more mass energy and floating around than in the other place. And so you would get a flow through the wormhole from one end to the other of this mass energy being transported. Right. And there's a wormhole property that's not widely known. It was something I was putting a lot of emphasis in during my talk, called back reaction, which is basically that the local laws of physics have to be rigorously conserved at both ends, no matter what you're doing in terms of putting a mass energy or charge or any other conserved quantity through it. So if you send mass through a wormhole, the wormhole end where the mass goes in gets heavier to keep the same amount of mass in this local region. And on the other end, where mass comes out that hadn't been there before, the wormhole has to lose mass in order to compensate for that. And so because of this process, if you have a flow of mass energy through a wormhole from one place to another, the exit end might very well develop a negative mass. And so this brings up the interesting question: is it allowed for a wormhole to have negative mass? And in my science fiction novel Fermi's Question, I assumed that no, when the mass goes to 0, the wormhole pinches off. But in our paper in Physical Review D, we assumed that it was possible to have wormholes that had negative mass, and even negative mass on the order of the mass of a star. At that time, which was sort of in the early 90s, there was a group of astronomers who was trying to solve the dark matter problem by hypothesizing that there might be something called machos, which are massive cosmic halo objects, which are out there, sort of dead stars that don't emit any light, but have the dark matter problem. And so they were actively looking for background stars, where in the situation where you have a background star and one of these machos passes in front of it, and by gravitational lensing produces a certain light pattern where the light abruptly gets brighter and dimmer as the macho goes by this background star. So we realized that if you had a negative mass object like this, you would get a very different gravitational lensing problem, which would be very characteristic, and that you could look for wormholes left over from the Big Bang by looking the same way that these guys were already doing. So we published the paper that represented a paper, and I contacted a friend of mine who's one of the people who was involved in it, and they included the programming for looking for, we call them gravitationally negative cosmic halo objects, which comes out to be ganachos. We convinced the macho people to look for ganachos as well as machos. They didn't find any, but otherwise, I guess I would have gotten a free trip to Stockholm or something. But they didn't find any. But we can say that there was an honest search for wormholes left over from the Big Bang as a result of our work. So I was kind of happy about that, at least.
A ticket to Stockholm may still be in the offering if your studies into the use of wormholes as time machines pans out. So maybe we can turn our attention there. I think most people who have heard of wormholes are familiar with the utility of wormhole as a convenient way of getting from point A to point B without having to, travel that distance in conventional space, and that in that way you could actually travel faster than light. But the idea that a wormhole could also be a time machine, I'm not sure how well known that is. Can you explain how that works? Is every wormhole, just because of the way a wormhole gets created, or in theory at least, would be a time machine, or does some kind of special additional factor
you have to do something
present? Yeah,
you have to do something to make it a time machine.
Okay.
And this is not my idea. This is the idea that Kip Thorne and company put into their physical review letter when they first published it in the 1980s. The basic idea is that there's a phenomenon called relativistic time dilation as part of special relativity. If you have an object that's moving near the speed of light, its clock slows down. And so they had the idea that if you had a pair of wormhole mouths in your laboratory, which are just connecting one place to another, and you took one of these wormhole mouths and put it in a relativistic spaceship, which was heading out for, say, in the direction of Alpha Centauri or something at nearly the speed of light, and sent it out for a while, and then turned around and came back and brought the wormhole end back into the laboratory, that end would have experienced less elapsed time than the one that stayed behind. And so instead of connecting 2 points in space, they would connect 2 points in time. And you would therefore make a wormhole into a time machine. This was a very interesting paper because before this was published, no physicist, no theoretical physicist would dare submit a paper to the general literature about time machines. And after this paper was published, suddenly there was a huge explosion of physics papers about time machines, and by theorists who were sort of trading on this idea in one way or another. One of the physicists who put their finger in the pie was Stephen Hawking, who suggested that if you look at some of the equations of quantum field theory and quantum electrodynamics, there are places where there's what's called a space-time interval in the denominator of the equation. And if you had something that was about to become a time machine, that space-time interval would become zero, and so you'd be dividing by zero in the equation. And he hypothesized that what that's trying to tell you is that the fluctuations of the quantum vacuum would sort of explode if you were about to create a time machine. And so he suggested that there's something called chronology protection, in which nature is basically protecting us from having time machines by destroying anybody who's trying to make a time machine out of a wormhole. Of course, this is not anything that's ever been tested, and so we don't know whether it's correct or not. But this was Hawking's contribution to this discussion.
Is this related to sort of philosophical or logical concerns with time travel, the so-called grandfather paradox, for example?
Yeah, well, it's a way of avoiding having to worry about grandfather paradoxes, because if nature automatically destroys any time machine that you try to make, then you don't have to worry about grandfather paradoxes. I guess that's one way of putting it.
And it's also
there have been other people who have tried to, including Robert Forward and I think even Wheeler and Feynman, who considered the possibility that there could be some kind of a time-like loop in which things connect back to themselves through space-time. And their conclusion was that as long as all the laws of physics are obeyed, that you don't do anything. But if a time-like loop verges on violating the law of physics, then it can't exist. And so they would solve the grandfather paradox by saying it's not possible because it would violate physical laws. But you need somebody to be your grandfather. You can't kill them and still exist. And so they would say that whatever solution came out of a time machine situation, it would have to be self-consistent.
The other debate it raises is, of course, questions of free will. And so while you can imagine a situation where time travel is physically possible, even logically possible because of those kinds of constraints, it would inevitably impact on what we conventionally have thought of as our freedom to make spontaneous decisions, whatever that actually means, because philosophers haven't really ever defined free will in at least to me, in a very satisfying way. But do physicists think a lot about those kinds of questions, or is that kind of left?
There's a concept. Well, okay, as you probably are aware, there's a lot of problems with quantum mechanics in terms of the paradoxical situations arising there too. Not so much time travel, but other kinds of things. And some of the ways of approaching this are by something called the block universe, where it is basically assumes that all parts of space-time are simultaneously existing, and we're just sort of moving along in a plane that goes from one to the other,
Yeah.
and experiencing things, and we think we have free will, but really the universe is all a solid block from top to bottom, and we can't really do anything to change that structure, even though we have the illusion of free will. I find that very unsatisfactory myself, and I don't like it at all. And my approach to quantum mechanics avoids that kind of nonsense. But it's amazing what people who are trying to solve problems in physics will be willing to believe in order to do it. And I've never been. I've always been sort of amazed at what some people are willing to swallow in terms of ideas like that.
Now, you've actually been involved in experiments to look at whether at the quantum scale there's evidence of what's called retrocausation, where if effects
right.
precede causes. That's really fascinating to me. Can you talk about some of the experiments you've done and what your findings have been?
It's an interesting situation. There is a property in quantum mechanics called non-locality, which is related to the Einstein-Podolsky-Rosen experiments and so forth, where you have two entangled photons and you separate them and you do a measurement on one, and it causes some change in the behavior of the other one. One way of saying it is if you do a measurement on the photon that it measures its wave-like properties, it forces the one on the other end to be a wave. And if you do a measurement on the photon that examines its particle-like properties, it forces the photon on the other end to be a particle. Okay. And there were some experiments that were one particular experiment, an experiment that was done in Maryland and another experiment that was done in Innsbruck that looked like that you had a situation where if you did a measurement on one of the entangled photons, you could cause the second entangled photon to either produce an interference pattern, a thing that goes up and down, sort of a wiggly pattern, or not, depending on what you did to the other guy. And so that looked to me like a mechanism by which you could do what's called non-local communication. You could have the two photon measurements separated by a long distance, and what you did on one of them would if the arms were the same length, would immediately appear on the other end, indicating not only faster than light communication, but also back in time communication if you play the length of the arms correctly. So I presented this at an American Association for the Advancement of Science meeting in San Diego as a paradox, expecting that somebody in the audience would say, oh, it's obvious why that won't work, blah, blah, blah. And rather than that happen, a lot of my colleagues at the meeting said, hey, that's a wonderful idea. Why don't you try it? And so I couldn't understand why it wouldn't work. And well, I was pretty sure that nature was not going to let you get away with it. But so I went back to the University of Washington and talked to some of my colleagues who do quantum optics. And there was a guy named Warren Nagurney who was a staff member and I guess he was an instructor in the physics department. He didn't have a tenured position. And he said, A, I will help you, and B, the National Science Foundation gave us money to build a laser lab in the basement 10 years ago, and the postdoc who's been using this lab just left to take another job, and it's available, and we can try to set up your experiment and try it. So that seemed to be, although I probably should have said no, that was an offer that looked like it was too good to refuse. And so I did that and spent about 3 years trying vainly to make this experiment work. And I had a lot of problems with noise in the apparatus, and there was a new technique where you could sort of eliminate the noise. Detecting single photons in the optical region is really hard. I mean, it's very easy to detect gamma rays or things like that have a lot of energy, but when the energy gets down to the order of an electron volt, it's really hard to measure such things. And there are devices that do it, but they're intrinsically noisy. And there was a new device involving a superconducting transition that looked like it was a way of noise-free detection. So I thought maybe this was the way of making this experiment that I was trying to do work. So I went to Vienna with my wife and spent a couple of weeks in Anton Zeilinger's laboratory talking to him, because he had just been starting to use this technology, and also arguing with him about whether it was possible to do non-local communication. And he presented me with a paper that had never actually been published by his group, in which there was some mathematics that turned out to be very useful. And I was able to go back to Seattle and take this experiment I was trying to do and analyze it do a very analytic quantum analysis of it. And after flailing around with that for maybe 9 months and enlisting the help of another physicist named Nick Herbert, I realized what the answer was, why it was that this seemingly, this way was where you could seemingly send messages by non-locality wouldn't work. And the answer goes like this. It requires you that on one photon you do a measurement, okay? Anytime you do a measurement, there's more than one possible outcome. Usually there's at least two. And you could show mathematically that if one of these outcomes was correlated with an interference pattern that looked like this, then the other one was correlated with an interference pattern that looked like this and filled in the gaps. And since the receiver at the other end of the message didn't know which of the two ways the measurement came out, he saw a superposition of this interference pattern and this interference pattern, which looked like just a broad lump with no interference at all. And so nature, which is doing all of these non-local things and sending messages faster than light and backwards in time, will not allow us to do that, to get in on her message system, because she
no
carefully
information
cancels out
can truly
the
be
signal.
transmitted.
And so that was what I learned from this time, that nature indeed is sending is inducing correlations that happen faster than light and backwards in time, but there's no way we can get on the action to send our own messages. And that was interesting. And I published a book in 2016 called The Quantum Handshake, and one of the chapters is devoted to discussing all the things that look like they make possible quantum communication, and then demonstrating the theorem that shows that it's not possible. I was pretty sure it was not going to work when I first got into the business, but I was intrigued by what could possibly be the showstopper that would keep you from doing it, and that's what I found out. And like it or not, it didn't work.
Has it led you to conclude that this is an area that is, definitively settled, or are there still? Can you still see new experiments to probe other approaches to retrocausality?
Let's put it this way: the quantum mechanics was when quantum mechanics was first being formulated, the founders of quantum mechanics built into it. They assumed that faster than light communication was impossible, and used this as a way of generating the formulation. So it's not surprising that the quantum formalism won't let you send messages faster than the speed of light. There's been some philosophers of science who've said that this sort of no signal theorems in quantum mechanics are tautologies, because it was built into the formalism by the founders, and so it's not surprising that you can prove theorems showing that non-local communication is impossible, which is what Nick and I managed to do, is the thing I was talking about, and which other people had previously done in various more theoretical and abstract ways. But it may be possible to reformulate quantum mechanics where you don't make these sort of biasing assumptions in the first place, and generate a new version of quantum mechanics, which is sort of a more general version of quantum mechanics, which might lead you to discover ways in which non-local communication was possible. The other thing is that the assumption is that quantum mechanics has a property called linearity, and this is a mathematical term. It's not exact. It sounds like it's talking about things in straight lines, but it's a lot more complicated than that. But there have been suggestions that maybe in certain domains might be nonlinear. the Nobel Prize winner Steve Weinberg investigated this in some detail a while back, and a whole lot of condensed matter physicists did experiments suggested by Weinberg to demonstrate that quantum mechanics is very, very, very linear in their area of expertise. On the other hand, if quantum mechanics was to go nonlinear, you'd expect it to be in places where the energies are very high and the energy densities are very high. This is more like CERN physics than it is like tabletop physics at a university.
Right.
And as far to my knowledge, nobody has ever tested the linearity of quantum mechanics in the ultra high energy domain at places like the LHC. And so if you are going to find a place where quantum mechanics break and you find a way to do non-local communication using some exception to the usual rules of quantum mechanics, that would be the place to look. But I have no idea what experiment you'd have to do in order to test that.
So, Professor Cramer, in our last few minutes, I wanted to change gears quite a bit here. You're sort of known for pioneering our frontier exploration of physics, but you're also a science fiction writer, and so you use that frontier thinking in your narratives in terms of probing some really big questions in the world of fiction. And you, in fact, your presentation that I referred to earlier at the University of Toronto was called "The Use and Misuse of Wormholes in Hard Science Fiction." So what are some ways that, now that we understand better what wormholes are, what they're not, and whether they may or may not actually exist, what are some ways in which wormholes are misunderstood by science fiction writers? How do they get the idea wrong?
Well, what they mainly get wrong is the fact that they were not aware of this back reaction property that I was talking about.
Okay.
For example, there are science fiction novels where there you have a wormhole between two planets, and you have trains running through, and so forth and so on. For another example is Paul Anderson had a novel in which he had a starship with a wormhole on board, and you fed reaction mass through the wormhole to shoot out the back and make the starship go faster and faster. That won't work because of back reaction. The wormhole would lose masses at the same rate that the reaction mass came through, and you would have no net gain in reaction mass as a result of sending stuff through a wormhole. So so as far as I can tell, everybody who's used wormholes as a prop has blown it because they haven't taken into account the idea of back reaction, except in my novel Einstein's Bridge and my new novel Fermi's Question, in which the back reaction is a very important part of the wormhole physics that's described there. And in Fermi's Question, among other things, I was talking about relativistic time dilation and wormholes. If you took a wormhole and kept it small, as close to a fundamental particle size as you could manage, and you sent an electric current through it to give it an electric charge, you could in principle at least, produce an object that looks that has the same mass and to charge ratio as a proton does. And if you had such a wormhole, you could put it in a big accelerator like the LHC and accelerate it up to a Lorentz factor in which its time is very, very dramatically dilated by a factor of 10 or 100 or 1,000 or even 1,000,000. Mm-hmm. If you then had one of these high-speed wormholes that you produce in your accelerator and you send it out into the universe and look through it, what you would see coming from the light coming back through the wormhole as it went through space would look for all the world like the wormhole was traveling at 10 or 100 or 1,000 times the speed of light. And if it would reach out, if you, for example, use the RIC accelerator at Brookhaven to accelerate such a wormhole, you could get a Lorentz factor on the order of 100. And so instead of getting to Alpha Centauri, which is a few light years away, in a few years, because the thing's moving in nearly the speed of light, you'd get there in a few days, as far as looking through the wormhole is concerned. So you could use this to explore the universe by sending out wormholes in various directions and using this relativistic time dilation. Now, what's actually going on here is the wormhole is becoming a time machine and sending signals back through its little time machine to you long after it took years to get someplace, it would be sending them back to you almost immediately, so you could see what was happening in advance. But this would not violate Hawking's ideas about making time-like loops, because there would be no loop to close. It would be sort of a one-way passage. And so this is an idea that I explored in some detail in my new novel, Fermi's Question.
I want to thank you so much, Professor John G. Cramer, for joining us here at the Star Spot and sharing a really fascinating conversation today.
Well, thank you. I really enjoyed it.
Thank you for joining us at the Star Spot, Mind and Universe continually expanding.
The Star Spot with Justin Trottier is an astronomy and space-themed podcast based out of Toronto, Canada. Please send comments or questions to starspotpodcast@gmail.com. The Star Spot is produced by Ying Zhang Li. Marketing and promotions by Natalie Morkos. Guest hosting by Denise Fong. News production by Benjamin Jenkins. News contributions from Julia Mazurchuk, Mallory Warren, Jessica Campbell, and Victoria Duncan. Web design by Blair Renault, graphics by Carmina Svillins. And I'm your host, Justin Trottier. Thank you for listening.